qualitatively, we've been looking at a graph of phase changes and temperature changes, looking something like this, where at each section of the graph, we can kind of get an idea of what's happening to the particles as heat is being added over time. As time goes by, heat is absorbed. And we start with the solid phase, we increase the temperature. As temperature increases, the kinetic energy increases, the particles move faster. But then we said that there's a plateau at the melting point, and that's where the energy added is used to overcome intermolecular forces. That's where we change phase. Then once all the particles have changed phase, the temperature can increase again through the liquid phase, where the particles are just increasing in kinetic energy, they're moving faster. We get to the boiling point, where we again need to overcome intermolecular forces, so there is still energy being added, it's just used for a different purpose than when the temperature changes. Now again, we got to separate those intermolecular forces, and once they've all been separated and the particles change from liquid to gas, we're all in the gas phase, and we can increase the temperature. Now we want to look at quantifying those different sections of the graph, how much energy is being added at each section of the graph. To calculate energy changes in association with a phase change or a temperature change, there are three equations we'll look at. They're all really easy, they're plug and chug. I'll give you these equations for any test or quiz. The first one is on specific heat. By definition, specific heat is the amount of energy required to raise 1 gram of a substance up 1 degree Celsius. Now it's a constant. You look it up on a chart. So on the next page, like here's a chart of specific heat values. Now what's interesting is that they're in units of joules per gram degree Celsius. That's kind of important. And so for example, liquid water. This one's real common. We'll use this one a lot. Liquid water has a specific heat capacity of 4.18 joules per gram degree Celsius. That means that it takes 4.18 joules of energy to raise 1 gram of water up 1 degree Celsius. Joules is a unit that we'll use to measure energy. It could be joules or it could be kilojoules. This specific heat here is measured in joules. Now, if you look at all the substances on this particular chart, do you see how liquid water is the highest? It's kind of interesting. Why would liquid water have such a high specific heat capacity? And we mentioned that if there's ever a question about water, you're not sure the answer, it probably has something to do with hydrogen bonds. Yes, it's all about hydrogen bonds. Water molecules have those strong attractive forces between them because of the oppositely charged ends of a water molecule. And so here might be my water molecule with the partially negative oxygen end and the partially positive hydrogen ends. And if you have a whole bunch of water molecules together, they're all very attracted to each other. They fill in the little nooks and crannies, which is why water in the liquid phase is more dense than water in the solid phase. Solid water is real crystalline, where the particles form like this very rigid crystal structure. And there's actually some little air pockets in between the water molecules in the solid phase. But in the liquid phase, the particles can flow and move past one another, and they really get as tightly packed as they possibly can because of those strong, attractive hydrogen bonds. And so it takes a lot of energy to start moving around those water molecules because, again, they're so attracted to each other. Then you look at, all these metals like iron down at the bottom. Iron's specific heat is like 0.449. It's pretty low, meaning that it does not take much energy to start increasing the temperature of iron, which I guess is a good thing if I want to use iron or like copper pots for cooking. I want something that'll increase in temperature quickly. It takes like 4 times as much energy to start increasing the temperature of liquid water as compared to iron metal. That darn specific heat. Okay, so these are constants. We look them up on a chart. And now watch how easy this equation is. So the specific heat of water was 4.18 joules per gram degree Celsius. Water in the liquid phase. Well, what if you have more than 1 gram of water? Well, then you take the specific heat and you multiply by the mass that you do have. And what if you want to increase the temperature by more than 1 degree? You multiply by your temperature change. So here's this cute little equation. It's just plug and chug. Delta H, your change in heat, is mass times temperature change times your specific heat, which again is a constant. This value is a constant. And you'll find it on a chart. Check the chart. I'll give you the chart for the thermal test. You just look them up. Now the other thing that technically we should mention is that temperature change is temperature final minus initial. And now sometimes we could get the temperature change off of a graph. Sometimes they might just give me the temperature, final and initial. So for example, this little graph at the bottom says we have an energy diagram for 25 grams of water. Calculate the amount of heat absorbed at each section of the graph. So whenever there's a temperature change, so like for example down at this first part of the graph, throughout the solid phase, delta H will be mass times temperature change times specific heat. We can use this equation whenever there's a temperature change. And then you just plug in your variables. So my mass is given 25.0 grams. My temperature change is technically 0 minus negative 20, or a 20 degree temperature change. And then for water, you just have to be a little careful because water has a different specific heat depending on its phase. That's not normal. Most substances just have one specific heat. So for water, I need to know that I am at the solid phase, and I look the specific heat up on a chart, 2.077 joules per gram degree Celsius. There you got it. You plug it in your calculator. And as far as sig figs go, I don't know. I'm not going to be super picky here. I don't know if this is maybe like 2 sig figs and 3 and 4. So when I put this in my calculator, I get like 1,038.5 joules. And maybe for now, I'll just leave it at that. When you take a test or quiz, they'll tell you how many significant figures to use. There, you're liking this, right? Little change of pace from stoichiometry. I can also use this equation throughout the liquid phase. So this middle section of the graph, same gig. Delta H is mass. It's still 25 grams. My temperature change is 100 minus 0. 100 degree temperature change. And then I need the specific heat of water in the liquid phase. And I look it up on a chart, and it's the 4.18 joules per gram degree Celsius. So we plug this in our calculator, and I'd be looking at about 10,450 joules. Your final unit will be joules because the specific heat is given in joules. So essentially it's kind of like the grams will cancel and the degrees Celsius will cancel. And so the only unit you have left is joules. Nice. And we can also use this equation way up on top in the gas phase. So, oh boy, let's say this is maybe like 115. It's definitely less than 120. So we'll kind of estimate. Plug and chug, same equation. 25 grams is my mass. Temperature change, final minus initial. So 115 minus 100. We'll say a 15-degree temperature change. And then specific heat, I can find on a chart. This is the gas phase, 2.042. And the unit is that joule per gram degree Celsius. There. Plug her all in. I mean, how could you possibly screw this up, right? How about like 765.75 joules? Awesome. Easy. This equation is used whenever there's a temperature change. Now there are two other sections of the graph that we kind of skipped. So here's my melting point, and way up on top I'm at the boiling point. We cannot use this equation to calculate the energy change because there is no temperature change. But the misconception is that if there's no temperature change, there is no energy change. So like on the test, it could be a multiple choice question, and they might say, how much energy is absorbed at this section of the graph? One of the choices is probably 0, to try to trick you into thinking that because there's no temperature change, there must be no energy change. And that can't be right. These are when we're changing phase, but yeah, we need to add energy to melt a solid, or I need to add energy to boil my liquid water, but we need a different equation. Because yeah, we can't use this one. There is no temperature change. So here's the other two equations we'll use. Heat of fusion and heat of vaporization. Heat of fusion is defined as the amount of energy needed to melt 1 mole of a substance. So fusion is for melting. Heat of fusion. Energy required to melt 1 mole. And way back at the beginning of this thermo unit, we mentioned that anytime you want to calculate an energy transfer, a change in heat energy, you need to know the quantity. Heat is dependent on the amount of substance you have. And that quantity could be given to us in either mass, which would be grams, or moles. So the mole is back. I mean, the mole really never left, right? It never will. And so again, these are constants. You look them up on a chart. There is a chart later on in our study guide. If I flip a couple pages and look for an example, here's one. Let's use 6. 6 kilojoules per mole is the specific heat, or not specific heat, heat of fusion for water. It means that it takes 6 kilojoules to melt 1 mole of water. And so look at this equation. What if you have more than a mole? Then you take your heat of fusion and multiply by the moles that you do have. Or what if I had like half a mole? Then I'd take 0.5 times 6. It would take 3 kilojoules to melt half a mole of water. It's brilliant. The equation just makes sense. The same thing is true with this heat of vaporization. It's defined as the amount of energy needed to vaporize 1 mole of a substance. Change it from a liquid to a gas. So again, if I flip ahead a couple pages, there's a chart. 40.6 kilojoules per mole is the heat of vaporization for water. So it requires 40.6 kilojoules of heat energy to vaporize 1 mole of water. And so look at the equation. They're really the same equation. The difference is just what phase change are we doing? Are we melting or are we vaporizing? Which would include evaporation or boiling. And all you got to do is look up that constant. So these guys are constants. And this is a constant. that you will find on a chart. And I will give you all those constants for any test. All right, so here's what it looks like. Let's go back to this graph, and we'll wrap it up. So this first section of the graph that we skipped, the first plateau, that should be the melting point. So the equation I'm going to use, delta H equals moles times heat of fusion, which does mean that I need to calculate moles. Oh, fabulous. So earlier in the problem, they told me that I have 25 grams of water. So let's take that 25 grams and we'll quick switch it into moles. Cancel grams. We want moles. 1 mole of water contains 2 hydrogen and 1 oxygen. So if I add them up on my periodic table, it's a little over 18. And, oh gosh, let's keep it at like 3 sig figs. 1.39 moles. All right, so let's plug and chug again. We got our moles, 1.39. And then the heat of fusion, I just looked up. It was 6 kilojoules per mole. So again, the equation kind of makes sense. It takes 6 kilojoules to melt 1 mole. I've got a little more than a mole, so we'll multiply. And I'd be looking at about 8.34. And now this one's in units of kilojoules. I know it's kind of annoying that the constants are in different units. We'll deal with it. But that one's got kilojoules. The specific heat is in joules. I'll deal with it. And now the beauty of this is, once you solve for moles, we can use that number again up here at the boiling point. So when we're up here at the boiling point, the equation I want to use, delta H equals moles times heat of vaporization. But it's still 25 grams, so it's still 1.39 moles. I just need to look up the heat of vaporization on a chart. And for water, it's 40.6 kilojoules per mole. So we plug it in our calculator. And it's maybe like 56.4-ish. And then that again is in kilojoules. How cool is that, huh? Not bad. I like this. So there's how we'd use these 3 equations to calculate energy changes associated either with a phase change or with a temperature change. Now they could ask me, what is the total amount of heat absorbed to take 25 grams of solid ice at negative 20 degrees all the way up to steam at 115 degrees Celsius? What if they asked me for the total amount of energy absorbed? So you're probably thinking, oh, just add them up, right? Absolutely, just add them up. The only thing you need to be careful of are the units. If I'm ready to add, I need to make them all joules or all kilojoules. So maybe we'd end up changing that to like 8,340 joules or 56,400 joules. So that once I'm ready to add different sections of the graph, they're all in the same units. Piece of cake, huh? So then we're just going to use these equations throughout the next couple videos, and we'll see what we can change and have a little more fun with these phase change equations.